Friends, I welcome you all to my channel. A 7-ton steel behemoth accelerates across the proving ground, gathering speed. 25 kilometers per hour, 30. The driver jerks a lever. On the sides of the tank, 4 giant metal wheels begin to rotate. They strike the ground with such force that the machine detaches from the earth and soars into the air. The Soviet tank is actually jumping. These are not frames from a science fiction movie, nor is it a mad stunt for a film shoot. This is a real test of a combat machine created by engineers in Leningrad in 1937. A tank that was supposed to leap over trenches and ditches like a frog over puddles. By the mid-30s, tanks had already proven their effectiveness on the battlefields. Tracked machines broke through defenses, supported infantry, and struck terror into the enemy. But one fundamental problem haunted military engineers the world over. Wide anti-tank ditches and deep trenches turned even the most powerful tanks into helpless piles of metal stuck before an obstacle. An anti-tank ditch was an engineering structure with precise parameters. The depth had to be at least 2 meters, and the width from 3.5 to 5 meters. These dimensions were not chosen by chance. A tank would approach the ditch, try to overcome it, and either get its nose stuck in the opposite wall or fall inside entirely. The machine became a stationary target for enemy artillery. The crew found themselves in a trap. In the USSR, they tried to solve this problem in many different ways. Some designers suggested making tanks longer so the hull could bridge the width of the ditch. Others developed special bridge layers. Still others experimented with additional tracks, enlarged rollers, or special fascines made of logs. All these solutions had one critical flaw: they made the tank heavier, slower, more expensive, and more difficult to produce. In the summer of 1937, engineer Vasily Vasilyevich Linzer from the Design Bureau of Factory No. 185, named after Kirov in Leningrad, proposed an idea that seemed utterly insane. The tank should not drive across a ditch or trench. The tank should jump over them. Yes, exactly, jump. Lift all its tracks off the ground and fly over obstacles in free flight. Ordinary tanks could only hop when hitting a ramp or a sharp drop in height. Linzer, however, proposed creating a machine that could jump on perfectly level ground at any moment at the driver's command, using its accumulated kinetic energy of motion. How was this supposed to work? 4 huge eccentrics are installed on the sides of the tank. These are metal wheels of irregular shape with protruding lugs. The tank accelerates and accumulates energy of motion. The driver pulls a lever. The eccentrics are connected to the transmission through a system of clutches and begin to rotate rapidly. Their protrusions strike the ground with enormous force, pushing the machine upward. At the moment of liftoff, the drive is automatically disconnected. The tank soars into the air, and the accumulated energy carries it forward. But when more than 7 tons of steel fall to the ground after a jump, the impact upon landing would be monstrous. Linzer and his colleagues understood the danger. They developed a special driver's seat on powerful hydraulic shock absorbers, which were supposed to absorb the main energy of the blow. The seat was additionally equipped with safety belts. The driver buckled up like an airplane pilot. The factory management approved the project. If they could create a working prototype, it would become a true revolution in tank building. Soviet tanks would be able to overcome any anti-tank obstacles. The enemy simply would not be able to stop such machines with traditional engineering barriers. Wide ditches, jump over them; high embankments, leap over them; log jams, fly above them. The project received the official designation TPP-2, an obstacle overcoming tank. Work began immediately. The designers had to solve many technical tasks, create a reliable system of eccentrics, calculate the optimal acceleration speed, and ensure the driver's safety. But the main thing was to prove that the very concept of a jumping tank was workable. Theoretical calculations showed that for a successful jump, the tank needed to accelerate to approximately 25 kilometers per hour. At this speed, the kinetic energy should be enough for a flight over a distance sufficient to clear a standard ditch. But what would practice show? As a basis, the designers took the T-26 light tank, one of the most mass-produced machines of the Red Army. It was chosen for its relatively simple design and well-studied technical base. Most importantly, it could be seriously lightened. Weight was a critical parameter. Every extra kilogram meant the need to develop a higher speed before the jump. The only way out was to lighten the machine as much as possible. The designers engineered the eccentrics, thought out the drive system through clutches and shafts from the engine, and calculated the characteristics of the hydraulic shock absorbers for the driver's seat. If they were too soft, they wouldn't dampen the blow. If they were too hard, they would transfer it to the spine. Every detail required careful development. Ahead was the creation of a prototype, long months of work and testing. No one knew if it was even possible to make a tank jump. Perhaps this whole venture was doomed to failure, or perhaps the USSR would truly create a revolutionary combat machine capable of jumping over any obstacle. In the autumn of 1937, work on the prototype began at factory number 185. The designers took a serial T-26 and began its radical transformation. Every saved kilogram gave a chance for success. The turret was removed and discarded. It weighed several hundred kilograms and was not needed for testing. The gaping hole in the turret box was welded shut with ordinary steel plates. The armored roof of the hull was replaced with thin steel sheets. Turret box details were removed. The ammunition rack with its brackets was dismantled. The armored fenders over the tracks were cut off. The designers went over the tank like a sculptor over a block of marble, cutting away everything superfluous. The internal equipment of the fighting compartment was thrown out. Spare barrels, toolboxes, extra canisters, everything disappeared. They decided to fill the fuel tanks only to 1/3. 300 liters of gasoline weigh nearly 200 kilograms. Pouring in 100 liters saved another 130 kilograms. After such a diet, the curb weight was 7 tons and 276 kilograms. The serial T-26 weighed 8 tons. They managed to shed more than a ton. The power plant was kept from the base tank. A Gaza T-26 gasoline engine with a capacity of 90 horsepower. It was supposed to not only move the tank but also spin up 4 massive eccentrics. From the engine, through a system of clutches and shafts, the drive went to the eccentrics. The driver could pull a special lever, the clutches would engage, and torque would go to the eccentrics instead of the tracks. The eccentrics themselves were 4 metal discs of complex shape, 2 on each side. Each had massive lugs that were supposed to catch the ground. They were attached at the points of the suspension bogies. The loads during the jump were expected to be monstrous. The eccentrics would strike the ground with a force of several tons. The diameter of each was about 1 meter. When they were installed, the machine began to look fantastic. 4 giant wheels with teeth protruded from the sides. The width of the tank grew to 3 meters. The serial T-26 had a width of 2 meters and 44 centimeters. The length remained the same, 4 meters and 60 centimeters. The height decreased to 1 meter and 70 centimeters. The result was a squat, wide machine that looked like a technical monster. The automatic disconnection system was critically important. The eccentrics were supposed to rotate approximately 1 turn, pushing the tank. If they continued to rotate, the result would be chaotic shaking. The engineers made a mechanical disconnector. After a certain angle of rotation, the clutches automatically disengaged. Special attention was paid to the driver's seat. The regular seat was replaced by a special construction on 4 powerful hydraulic shock absorbers. Each was a cylinder with a piston filled with oil. Upon impact, the piston enters the cylinder. The oil resists, absorbing the energy. Such a system was supposed to save the driver's spine. The characteristics were calculated carefully. If the shock absorbers were too soft, the seat would bottom out. If they were too hard, they wouldn't work. The seat was additionally equipped with wide safety belts over the shoulders and lower back. The driver had to buckle up like a pilot. The controls remained standard. 2 steering levers, pedals. Only the lever for engaging the eccentrics was added to the right of the driver. By the end of November 1937, the prototype was ready. Workers walked around it, staring at the protruding eccentrics. Someone joked that the tank looked like a beetle. Others compared it to a giant frog. Military representatives arrived for acceptance, inspected the design, and checked the documentation. The designers explained the operating principle and showed the calculations. The military shook their heads, whether in admiration or doubt. Checks began. The tank was set on a stand, raising the tracks, the engine was started, the transmission and gear shifts were checked, and the eccentric drive was engaged. The driver pulled the lever. A click of the clutches. The 4 discs began to rotate, gathering speed. Faster, even faster. The lugs sliced through the air with a whistle. The disconnector tripped. The clutches disengaged, the eccentrics slowed down, and the mechanics worked exactly as calculated. The starter, cooling, and brakes were checked. Everything was in order. Bench tests were successful. Now, the most frightening part remained. Take the tank to the proving ground, accelerate it to the required speed, and try to make it jump. Would it work? Would the driver survive if the machine jumped and crashed to the ground? November 26, 1937. A cold morning. Engineers, military personnel, and workers gathered at the factory number 185 test track. Everyone came to see the tank that was supposed to jump. The TPP-2 stood at the edge of the track. Its eccentrics protruded to the sides. The driver took his seat and started the engine. The task was simple. Accelerate to 25 kilometers per hour, engage the eccentrics, jump. Before heading out, they conducted checks, put the tank on stands, and the driver engaged a gear. The tracks spun in the air. Then he engaged the eccentric drive. The 4 discs rotated. The drive disconnected automatically. All systems were normal. The tank was taken off the stands and the machine moved. The tracks clicked against the concrete. 10 kilometers per hour, 15, 20, 23. It was time. The driver pulled the lever, a click of the clutches. The 4 discs spun up, receiving torque from the transmission. Their lugs touched the concrete and nothing. The tank did not jump. The tracks locked up. All the power went into the eccentrics. The machine sharply lost speed and skidded sideways, leaving black streaks on the concrete. The eccentrics slipped on the damp surface. Their lugs scraped without finding grip. A failure. The tank stopped. The engine stalled. The driver climbed out, frustrated. Instead of a jump, it was just a slide across the pad. Engineers rushed to the machine. One inspected the eccentrics, another checked the drive. The military took notes in their pads. What went wrong? The first problem was obvious. The speed of 23 to 25 kilometers per hour proved insufficient. Kinetic energy was not enough. The calculations had been too optimistic. The second problem was the surface. Smooth, damp concrete. The lugs slipped like wheels on ice. It needed earth, soil, something the teeth could bite into. The third problem: during the inspection of the mechanisms, colossal friction was discovered. Metal was peeling off in shavings. Scratches on the shafts were up to a millimeter deep, and there were scratches on the gears. A huge part of the power was lost. The engineers estimated that if the engine produced 90 horsepower and 20 to 30% was lost to friction, only 60 to 70 reached the eccentrics. Not enough to spin up 4 discs in a fraction of a second. The result of the first day was 0. The tank did not even lift off. The military drew up an act. The engineers began a meeting. Had the concept really failed? On November 27, the designers worked all night. They disassembled the drive, found the points of friction, lubricated the parts, and adjusted the clutches, hoping that an improved drive and higher speed would yield a result. The tank accelerated. The driver squeezed out the maximum, 25, 27, 28 kilometers per hour. Engagement of the eccentrics. They spun faster. Lubrication helped. They struck the concrete. The tank jerked. The front part rose by 10 to 15 centimeters for a fraction of a second and crashed back down with a bang. This was not a jump, a pathetic attempt to hop. The machine slid for a few more meters and stopped. The driver climbed out pale. He had been jolted by the fall. At least his spine was intact. The belts had held him. The designers inspected the tank. The picture was discouraging. Yes, the drive was better. Yes, the speed was higher. Yes, the tank had hopped, but this did not bring them closer to the goal, jumping over an anti-tank ditch. The list of problems grew. Insufficient speed, poor traction, high power losses. But another critical problem was discovered. The T-26 chassis had a rigid leaf spring suspension. It dampened jolts from bumps during normal movement, but was not designed for the loads of landing after a jump. Even if the tank jumped to a decent height, the landing would be monstrously hard. Leaf springs would not absorb the energy of falling 7,000 kilograms from 2 or 3 meters. The energy would turn into a shock that would destroy components. The suspension would begin to break, rollers would deform, tracks would fly off, shafts would bend, the hull would crack, and drivers risked spinal injuries. The designers gathered for a meeting. There were more problems than anticipated. Power was lacking. The drive worked with friction. Traction was insufficient, and the suspension was rigid. But the main problem was fundamental. The tank was too heavy, and the engine was too weak. The T-26 was not capable of reaching the speed of 30 to 35 kilometers per hour required for a jump. Its maximum was 32 kilometers per hour on a highway. The military asked questions, deadlines for improvements, guarantees of success, production costs. The price of a jumping tank would be several times higher than a regular one. The designers promised to fix the defects. They believed in the concept. The principle of the eccentrics was correct. They just needed to refine the parts. Maybe it would work. The tank was taken to the shop. The drive was completely disassembled. Friction was eliminated. Damaged parts were replaced, and the last unnecessary elements were removed. Work dragged on for weeks. Late November, December, the new year was approaching. The jumping tank stood in the shop, waiting for tests. The military was becoming impatient. Management inquired about deadlines. The designers worked day and night, hoping for a miracle. December 26th. A month had passed. Damaged parts were replaced, and the lugs were reinforced. The last chance. Winter had covered the pad with snow. A path was packed down and sprinkled with sand. A wooden floor was laid at the point of takeoff. Wood would give better traction than concrete. The tank was brought out. Acceleration on the snow, 28 kilometers per hour. The eccentrics spun up and struck the floor. The tank jerked upward, rose by 20 to 30 centimeters. The tracks detached. A jump. But a grinding of metal rang out. The eccentrics slowed down. The tank froze for a moment and crashed onto its tracks. The impact was monstrous. The leaf springs took all the energy of the fall. Parts snapped. The driver climbed out pale and shaking. An inspection revealed a catastrophe. The axle shafts of the eccentrics had jammed in the side tubes. Transmission parts broke, teeth were sheared off, and shafts were bent. Cracks appeared in the housings, leaf springs were deformed, and rollers were dented. One jump, and the tank was destroyed. What happened? The lugs bit too deep into the wood, got stuck, but continued to receive torque from the transmission. The colossal load bent the axle shafts and jammed them. The transmission did not hold. The tank had lifted off, but it was a pathetic hop. Height, 30 centimeters. Distance, 0. The machine fell back in the same spot. This was enough to destroy the suspension. The military looked at the crippled machine. The verdict was obvious. The end. No amount of refinement would fix the fundamental problems. December 31st, New Year's Eve. One last attempt. Somehow they patched it up. The driver was a different one now. The previous one had refused. He took his place. Once again the track, once again the floor, once again the acceleration. The eccentrics rotated. The tank jerked, rose by 10 centimeters, and fell. Symbolic, conditional, useless. Testing was stopped due to lack of progress and due to obvious futility. The Auto Armor Directorate issued a report. The conclusions were contradictory. On one hand, the tank confirmed the fundamental possibility of a jump. The concept works. Theoretically, eccentrics can push a tank. On the other hand, practice failed completely. A speed of 25 to 30 kilometers per hour does not provide enough energy. Rigid suspension makes landing destructive. The drive works with huge losses. The main conclusion was harsh. Further testing made no sense. The machine was to be transferred to the role of a factory tractor. Thus ended the story of the only Soviet jumping tank. Why the failure? There were several reasons. First, physics. To make 7 tons jump 3 to 4 meters requires enormous energy. The 90 horsepower of the engine was catastrophically little. Even after lightening, the tank weighed more than 7,000 kilograms. The engine could not accelerate it to 35 or 40 while simultaneously spinning up 4 eccentrics. Second, mechanics. The drive was too complex and unreliable. Friction losses, overloads, jams, breakages, even the 90 horsepower reached the eccentrics with colossal losses. Third, the base. The T-26 was a good light tank, but its chassis was not suitable for jumping. Rigid leaf springs could not dampen the impact. A completely different suspension was needed, soft, with long travel, and powerful shock absorbers. Fourth, time and money. The year was 1937. The USSR was preparing for war. Simple, reliable, mass-produced tanks were needed, not experimental monsters of questionable value. Even if the concept had worked, a jumping tank would have cost many times more. And the main thing, uselessness. Suppose the tank could jump 5 meters. What then? Anti-tank ditches were 3.5 meters wide. A 5-meter jump would clear a minimal ditch, but not a maximum one. The enemy could dig wider. Furthermore, a jump was a colossal stress. After each one, an inspection and replacement of parts was necessary, unrealistic in combat. The tank might jump once or twice, then go out of order. It was much simpler to use other methods, bridge-laying tanks, assault bridges, or fill in ditches with earth. All of this was more reliable, safer, and more effective than a hypothetical jumping tank. The prototype stood in the shop for a few more months. Then the eccentrics were removed, the transmission was put back in order, and a cargo bed was installed. It became a factory tractor for transporting parts. In this form, it served for several more years. The idea of a jumping tank was never revived. The designers abandoned the concept forever. Testing showed that physical laws cannot be cheated. You cannot make a multi-ton machine fly without catastrophic consequences. But the experiment was not useless. Valuable experience was gained, the limits of the possible were learned, and they understood which solutions worked and which did not. This experience was useful in designing other tanks, traditional, effective ones, those that fought and won. The story of the TPP-2 is a story of a bold idea that crashed into reality. Sometimes fantastic concepts remain on paper, and that is as it should be. Not every idea deserves to be realized. If you are interested in such stories of mad military technology, give a like and subscribe. Here, we break down the most absurd military inventions that seemed brilliant, but turned out to be a catastrophe. Until next time.